All right, let's dive into a coding puzzle that, I gotta say, trips up a lot of people, even seasoned developers. On the surface, it seems pretty simple. You just find a certain kind of sum inside a list of numbers. But the solution isn't about just grinding through it. It's all about this really neat little math trick that once you see it, just changes everything.
So here's the challenge for you. Imagine you're given a list of numbers and another number. We'll call it k. Your one job is to figure out if there's a continuous subarray, a connected slice of that list that has at least two numbers and where the sum is a perfect multiple of k. Sounds straightforward, but the real test, doing it fast.
Okay, so before we even think about writing a single line of code, let's get super clear on what we're actually looking for. The problem calls this a good subarray, and there are two crucial rules we absolutely have to play by.
Let's break this down. First, contiguous. This just means the numbers have to be neighbors in the list. No skipping around and cherry picking. Second, and this is important, the subarray has to have at least two elements. So a single number, even if it's a multiple of k, doesn't count. And finally, the sum of all those elements has to be a multiple of k. In other words, when you divide that sum by k, you get a remainder of 0. Oh, and a quick side note, 0 itself counts as a multiple of any k.
Let's make this totally concrete with a few examples. Look at that first row. Our k is 6. Well, if you look at the subarray 2, 4, what does it add up to? 6. That's a multiple of 6. It's got two numbers, it's contiguous. Boom! We return true. In the second example, the whole array adds up to 42, which is 7 times 6. So that's also a multiple. Another true. But in that last case, with k equals 13, you can check every combination, but you're never going to find a slice that adds up to a multiple of 13. So that one's a false.
Now, this all seems pretty manageable, right? Well, here's the kicker. This is the catch that turns a simple puzzle into a real head-scratcher. The input array we're given, it's not just a handful of numbers. It can have up to 100,000 elements. And that little detail is a giant clue that the most obvious solution is probably the wrong one. And that's exactly why the obvious approach is a total non-starter. Trying to check every single possible subarray, start here and there, add them up, check the remainder. For an array with 100,000 numbers, that's not just slow, it's basically impossible. It would take forever. We need a shortcut, a much, much smarter way to tackle this.
So if the brute force method is out, where do we find this clever shortcut? Well, it's not hidden in some super complex algorithm. The secret is actually in a simple piece of math that's been right in front of us the whole time. This is the real aha moment of the problem, and it's all about remainders.
To unlock this secret, we're going to use a concept called a prefix sum. Don't let the name intimidate you, it's really simple. It's just a running total. As we move through the array, we just keep track of the sum of all the numbers we've seen so far. Why do we do this? Because once you have these prefix sums, you can find the sum of any subarray with just one simple subtraction. It's the prefix sum at the endpoint minus the prefix sum from just before the start point.
Okay, so with that little tool in our pocket, we can rephrase our entire goal. We're not really looking for a subarray sum anymore. What we're actually looking for are two different prefix sums whose difference is a multiple of k. Or, to put it mathematically, that difference divided by k has to have a remainder of 0.
And this is the whole trick. This is the key. Think about it for a second. When is the difference between two numbers a multiple of some other number k? It only happens if those two numbers have the exact same remainder when you divide them by k. Like take 17 and 7 and say k is 5. The difference is ken, which is a multiple of 5. And look, 17 divided by 5 has a remainder of 2, and 7 divided by 5 also has a remainder of 2. When the remainders match, the difference is a multiple. It's a fundamental rule. This idea completely flips the problem on its head. We can forget about the actual sums. We don't care how big they get. All we need to do is calculate our running total, find its remainder when we divide by k, and then just ask one question. Have we ever seen this exact same remainder before? If the answer is yes, we found our good subarray. The problem is transform.
So this is a fantastic insight, but how do we actually put it into action? We need a way to efficiently keep track of the remainders we've seen, and just as importantly, the index where we first saw them. And the perfect tool for this job? A hash map. It's a data structure that lets us instantly check if we've seen something before. Let's see how it works.
Here is our game plan, step by step. First, we create an empty hash map. This is where we're going to store the remainders we see. Then, we're going to loop through our array, one number at a time, keeping a running sum. At each step, we calculate the remainder of that sum divided by k. Then comes the crucial check. We look at our map and ask, have we seen this remainder before? If the answer is yes, and if the distance between our current spot and that old spot is at least 2, we're done. We found it. If the answer is no, we just add this new remainder and its index to our map and move on to the next number.
But there's one really clever little trick we have to do right at the beginning. It handles a special case. What if the good subarray starts at the very beginning of the whole list? To catch this, we have to initialize our map with a special value, rec 0, -1. I know it looks weird, but think of it like this. We're telling our program, hey, we saw a remainder of 0 at index -1, before the array even started. It's a brilliant little hack that makes sure if our running sum itself becomes a multiple of k, our algorithm catches it correctly.
Okay, let's trace this step by step with a real example. We start with our special map, 0 - 1. We go to index 0, the number is 23. Our running sum is 23. What's 23 divided by 6? The remainder is 5. We haven't seen a 5 before, so we add it to the map. 5, 0. Okay, next up, index 1. The number is 2. The running sum is now 25. The remainder of 25 divided by 6 is 1. We add that to our map. 1, 1. Now, index 2. The number is 4. The running sum is 29. And what's the remainder of 29 divided by 6? It's 5. And now we check our map. Have we seen a remainder of 5 before? Yes, we have. We saw it way back at index 0. The distance between our current index, 2, and that old one, 0, is 2. That meets our rule of being at least 2 elements long. We found it. We can stop right there and return true.
Let's just pause for a second and appreciate what just happened here. We started with a brute force idea that was just completely doomed to fail on a large scale. But by applying a really simple mathematical insight, we came up with a solution that's not just fast, it's incredibly elegant.
And this slide right here shows you the payoff. The brute force approach is what's called ON squared. That means its runtime just explodes as the list gets bigger. But our new solution, it's ON, or linear time. We just have to pass through the array one single time. For a huge data set, that's the difference between an impossible wait and an answer that feels instant.
So the big takeaway here is this whole pattern, the prefix sum plus remainder trick. This is a total powerhouse technique for any problem that involves subarray sums and divisibility. Remember this combo. Use prefix sums to handle the adding, and use a hash map to remember the remainders. It can turn what looks like an impossibly slow problem into a lightning-fast one.
And that's what's so cool about problems like this. It kind of makes you wonder, right? What other simple, powerful mathematical ideas are just out there, hiding in plain sight, waiting to be applied? What other remainder tricks are ready to transform the next complex problem into a simple, elegant solution? Some to think about.